Vlad wants to see my ticket. Well, Black can suck a dick. He's as dumb as rocks, and rocks had little pricks.
All right, welcome everybody to, I guess we're calling this a conversation, if you will. Does Flat Earth have anything left, or is it done? I believe one of us believes that it is done, and one of us believes that it's still got legs and truth and facts and evidence and all that stuff. So we're gonna find out tonight. Have a little conversation with my buddy Alan from Space Audits. It is episode number 1. It is November 12th. If you're watching then, sorry we're late, or I'm late. It's not Alan's fault. I was at a auction in Fresno, and it went longer than I thought, so didn't get home till about 5. So 4 o'clock wasn't a good time to start. All right, let's bring him on, and we will get going. There we go. Oops, that's the wrong one. We'll get it right eventually here. And there we go. Boom. Alan, say hello, everybody. Tell them who you are, where they can find you, and all that good stuff.
Hello, everyone. I'm Alan from Space Audits and/or Ether Cosmology. We are one and the same, or synonymous, or whatever they say. So anyway, if you want to find our work and research, you can join our Discord at discord.gg/ethercosmology. That's ether with an A. And then my YouTube channel is at space_audits. So you can find our work there. We do weekly presentations on either flat Earth or ether dynamics.
Tremendous. All right. So I know we're just going to, basically shoot the shit. Try not to have any kind of moderation that we don't need. So I believe I'll let you start if you want to do like an intro, or how do you want to do that?
Yeah. So since the TFE, we've all been searching for an answer, right? Like none of us expected, or some people did, but most of us did not expect to see a 24-hour sun. And it really made us, rethink the paradigm, go back to basics. And I wanted to kind of touch base and share some of the research and things that have come along the way and regarding celestial and terrestrial measurements, and actually the history of flat Earth as told to us from the Chinese perspective.
All right. Can I ask you 3 simple questions to start, just so I get a feel for where you're at as far as did we go to Antarctica?
Yeah, I'm fairly certain you guys went. I don't contest that at all.
Yeah, no, it's just the main, the argument from most flat earthers is that we didn't even go. So that's a good start. And we did see the 24-hour sun. So you are of the belief that it takes place in the southern summer?
Yeah, and not only you guys, seeing it or whatever, but there's also record of the Chinese talking about it when they did their expedition in the 1400s. And and I also found some Greeks. It was I can't remember his name, Animaxenes or something like that, Anaxagoras or whatever. And Aristotle were one of those names, So anyway, Anaxagoras and Aristotle were getting into it, and Aristotle was like, "Well, what about the 24-hour sun in Antarctica, or in the southern half?" And he was like, "Well, I haven't seen it. I don't know if that's a real thing or not. But if it was, he basically invoked like terrestrial features that surround the Earth that would like block the sun at different times of year, kind of thing." That was his explanation for it, but he didn't seem to bother him too much. But yeah, the Chinese, which we'll get to in a bit, knew about it for sure.
So the first question was, did we go to Antarctica? You say yes. Is there a 24-hour sun? You say yes. Third question, do you believe that there's a South Pole that was 600 miles from where I was? Can we deduce that is in existence if we saw the South Celestial Pole, and we would have to assume what's underneath it? And we also know that people in different areas of the Earth can get there by all going towards the southern part of the sun. So do you believe that there is a South Pole?
Yeah, so I'm pretty sure there is. Like, you're just measuring latitude convergent lines, right? As they go together, and you would presumably have the same thing in the north. Like how it works mechanistically, we'll talk about the mapping of the world using the stars versus what an observer sees per their latitude. Because I think the difference is there. I think the difference there is that we see everything individually, but we're shown these 3D models that have a God's eye view that kind of give us an expectation of physicality to the heavens, and like if this thing's over here, then nobody should see it over here. But the whole entire thing is absolutely designed from the top or from the bottom up as an observer centric single observer to make the whole thing in both hemispheres. They used to have 2 separate star maps for the north and the south before they merged them together. But we can talk about that as we continue on.
Okay, yeah, just wanted to make sure. And then, props to you versus many of the other flat earthers that won't even have me on their show or won't even have a conversation and block me, everything else. So I just want to give credit where credit's due. At least he's willing to come on, have a conversation, and admit what the truth is, which is, yes, we went to Antarctica. Yes, there is a 24-hour sun. And I guess by extension, I say there's a South Pole. And we'll get into that. But I just want to make sure that those 3 things were covered. So you can go ahead and begin whatever you want.
Give me 1 second. Let me just add something to the
Sure.
for circumpolar stuff so we can talk about that later. Circumpolar orbits in travel. Okay. Circumpolar longitudinal orbits. Okay. So to start us off, I wanted to talk about the celestial theodolite and kind of give an update on that.
Okay.
So recently, a member of our Discord named Brian did his extended the application of the celestial theodolite using eclipses, and basically the premise, which we'll watch a video here in a little bit whenever you're ready for it, but it goes over all the details and stuff. And I would also like to get as many globe lads to get eyes on it so that they can refute it or point out flaws in the logic and whatnot. So but anyway, the basic. Go ahead.
What's the deal with that guy Jesse? So I know that he said that he thinks that there's lies within there, or that the numbers are fudged, or that it doesn't actually do what you say it does. When you say you have, you want to get as many glober eyes on it, have you considered having him look at it if he thinks that there's some sort of lie involved?
Oh, Dude, we've had endless back and forth with him, and he does like not to get in. I'm not trying to slander him while he's not here or whatever, but to like give you a truncated recap, he does things like conflate the analysis between the globe prediction for the observer and then for what we're doing. He calls it the same method. He built a simulator to cherry pick observations because, like, as we can get into it for the data, we're dealing with ratios of a triangle. There's should exist a location per each measurement where the globe would technically exist as for the measurement, right? And when we look into the data there, we can see exactly what he did going to sea level and then finding the lowest possible hill to do the occlusion at, and we could see the difference in the numbers and what actually came out because he went to a place where it's indistinguishable, not where it's one's better than the other. So, like, a lot of what he does is try to conflate things and make it so that nobody can get a conclusion or understand anything. So, like,
okay, would you be open to a debate with him then over that?
No.
If we had like on my channel or something? No. Okay.
No.
Because
yeah,
you've been through it a bunch of times.
We've been over it a bunch of times, and my last straw with that guy was the last self-theo that we did with him. He was asking for the equations that we were using for how we were doing our derivations. I gave him the equations. Mike gave him the equations. We sent him PDFs of the equations. Like, this is all happening in the same exact time. He's screen sharing on Discord, so he has Notepad open. He's written down the equations that I give him, and he's in Discord telling people that I won't give him the equations. Like, I'm not trying to deal with that. That's a level of like,
okay,
that's the equivalent of you didn't go to Antarctica.
Oh, yeah, that's what you're talking about. I mean, to me, if he's saying that it doesn't work like you say, or that it's cherry picked, or that, because I mean, really, what science is repeatable predictions, right? So the celestial theodolite should make better repeatable predictions than the globe, and I'm not sure it does that. From what I've heard, it's these couple times it works.
Yeah. So
I'm not trying to wait for you to.
No, you're good. There's a difference between that's not what I've heard versus I've looked at the data and I can confirm everything that's being said. That's an extremely important aspect of this whole thing because a lot of people are relying on what that guy says and what Ruhiv says. And
true. I mean, but I'll say that
getting it through a filtered lens of.
I'll admit that
of what they want you to see about it.
Okay, and is the truth still that we are not including refraction in this?
We're not including refraction in it because the occlusion process is a physical process. So in other words, refracted light isn't going to intersect a refracted mountain, right? Like, and I can show you some examples of what I mean by reflected.
Okay, I'll let you show me.
By that not intersecting. So in other words, it requires the physical intersection between the source and whatever the mountain in this case. So what they'll try and do is they'll say, well, I want to add terrestrial refraction to the mountain because that'll make it match what a theodolite measures, but that doesn't cause an occlusion. That doesn't tell us anything about the occlusion. That just raises the apparent level of what it is, does nothing. And then on top of that, the astronomical refraction, the same situation. If it's refracted light, it's not going to get occluded through a refracted image only when the source intersects, which you'll see as we go through.
Okay, and then so that video I saw from Goose, doesn't that show it that refraction does affect the view?
Yeah, that's our premise, that it affects it when the physical intersection occurs. Because what happens is it gets lifted up a little bit, and then the angle, which the physical thing that's emitting the light has to be a little further behind the object before it actually gets occluded. So we're saying, when we're not accounting for refraction, we're saying that between you and the mountain, the refraction doesn't matter because on the back end of the light that's coming from behind the mountain, when that stops coming to you, it's no longer being refracted over the mountain, right? Like, that's the basic. When we say we're not accounting for refraction, that's what we're not accounting for. When the star is no longer visible, it's no longer refracted. And we just want to know where the light source of it was at the time that it was occluded. It's like it's almost so straightforward that it can only be only through like misrepresentation can it be confused.
Okay, well, I hope you're going to show us as because that doesn't make sense to me. I mean, anything that you're looking at and it gets blocked, and it's just like the sun, right? The sun is, well, again, I don't know if you believe that, but the sun is said to be below the horizon, and we still see it. So it's up above what's blocking it because of refraction.
Yeah, they certainly do say that.
Okay. But you just disagree with that. Okay, gotcha.
Yeah. Just watching the sunset alone wouldn't tell you anything unique about the situation because what they're saying is either true or there's just a lingering effect due to optics, and then as the sun goes away, it can't power through the atmosphere that it's that's between us and the light source. So either way, the same
atmosphere has something to do with the sunset.
What's that?
Are you saying atmosphere has something to do with the sunset?
Yeah, there's light attenuation, like the makes an opaque layer and all that.
But if atmosphere had anything to do with it, then we wouldn't be able to predict the time, because we wouldn't know the atmospheric conditions. So you would not know what the sunset. I can tell you what the sunset will be on Friday or next Monday or in 3 years.
Yeah, but you're basing all that off the apparent position anyway, which is predicated on knowing the atmospheric conditions anyway. So whatever it happens to be is however much refraction there happens to be. What I'm saying is either way it sets, just watching it set doesn't tell us anything unique about the situation. Because there could be, because like our premise is the sunset is an optical phenomenon where you guys say it's a geometric phenomenon. Right? That's the big difference. And just
if it could be time, then which one would be true?
Well, just watching the time of it setting doesn't tell us anything unique.
No, what I'm saying is tomorrow, we know the sunset time tomorrow, right? But we don't know the atmospheric conditions. It has nothing to do with the sunset time. The sunset time is done geometrically, has nothing to do with the atmosphere. The atmosphere, if tomorrow ended up being a cloudy day, it's not going to change the time of the sunset.
Are you aware though that the whole model is that's not predicted; it's post-dicted off of when the sun
Sure.
returns. So after you have enough data and you can say that, like that's all it is. So what we're saying is that it's an optical phenomenon rather than a geometric. And just watching it and saying, but what about the prediction? It's a post-diction, so it doesn't. It literally can't tell us anything unique about the
So
situation.
give me
Just
another
saying.
example of what an optical phenomenon is. What's an optical phenomenon? Just give me one, so that I can see if we're talking the same thing. Because you're making it sound like if it's an optical phenomenon, then it would be it would vary due to optics.
Yeah, so like you take the example of when a car is coming at you and it has two headlights, but when it gets further away, it just becomes one headlight. So like
Okay.
that's facilitated by an optical phenomenon. It doesn't have anything to do with curvature or anything
Right.
like that.
And it has to do with the atmosphere, meaning that we couldn't predict the time that would happen because it would vary based on what the conditions were.
Okay, then
But
just make it solely based on an optical phenomenon. That way, the time's the same no matter what.
So I asked for an example of that.
The sun's the same thing in question that you're invoking. That's why it can't tell us anything unique. That's why we need another variable. So, for instance, if you were to do a self-theo occlusion with the sun in a mountain or whatever, like you can make some determinations based off of the true position versus the apparent to see how much refraction and whatnot is actually affecting the stuff. But just watching it alone tells us nothing.
But predicting it, that's what I'm saying. I mean, if we're just watching it, no, yeah, right. But we predict it. We know what the sunset will be tomorrow, and it has to do with.
We
didn't.
No, it goes in a cycle, bro.
Yeah, no, but that's because
that's called a post-diction. If you know
sure.
if you know it's cyclical and you know where its position's going to be 20, like that's not a prediction. That's just a cycle and a post-diction.
Okay, so you're saying because it already happened, and then we are predicting it in the future. It's a post-diction, not a prediction. Okay, so we know what time the sun's going to rise tomorrow or set tomorrow because it's happened on that day of the year in the past, right? So you're saying because we know that, we can predict the future, and that's the only reason we can predict it. But if there's two models at play, flat Earth and globe Earth, and one of them describes why it is that we can predict that, and the other one says it's atmospheric, which can't be responsible for predicting it. So then wouldn't there be a clear winner there?
Like I just said, take out the atmospheric effect. If you're not accounting for it either, then we could just reduce it down to either optical or geometric. It doesn't matter. Like it's the same situation. Just watching it tells us nothing about the truthfulness of either model. All right. Okay, so yeah, the goose video. So that was illustrating that the differences in the occlusion time and how that would affect it. So what we're saying is that when the star gets blocked, whatever refraction was occurring, it can no longer overcome the mountain. Whatever refraction or optical or whatever is happening, it no longer overcomes the mountain. And we want to know where the true position of the star was with respect to the mountain peak at that time, because that's what is aligned for us with our field of vision. So we need to know, like if you think about that as the crosshair, like the mountain as a crosshair to the theodolite, so to speak, we want to know, or we go to the mountain peak to see where the stars align to see if it's still aligned with our crosshair. That's all we're doing.
Okay, I guess where I'm confused is that, so then can't we just call what you're seeing in the celestial theodolite an optical effect that it doesn't tell us anything about the shape of the Earth?
No, because there's a new variable there. There's an independent variable. So there's our distance relative to the control, which is the altitude of the mountain. So that's going to produce a unique angle, and that angle is going to be is dependent on the physical elevation of that mountain. So relative.
Where are you getting the information about what the angle should be? From Stellarium, right?
No, we're getting the elevation of where the mountain should be based off of like Wikipedia, like whatever the mountain source says. So Wikipedia, NOAA, any sort of reference that has the official numbers for the altitude of the peak.
Right, but where are you getting where the star should be in relation to that mountain?
Oh, yes. Yeah, from Stellarium.
Okay, which is globe-based, yes?
It's the nautical almanac that uses latitude and longitude, and all that is positions of the stars with respect to where they were at a specific time. So when we talked earlier, now the answer to your question, the quick, yeah, it's a globe tool or whatever, that would be like the easy layup, right? Because it's a sphere, right? All it's doing is showing you where the stars are at for an observer at their latitude. So it's again when I was talking about that God's eye view perspective that gives us that misconception, right? All we're looking at is where some dude took a zenith measurement of a star, and then 24 hours later that star came back to that position. So we're looking at a series of the whole model being put together like that. It doesn't mean that the Earth is a globe. They do a geocentric transformation to the center radius of the globe, right? But we'll get into fictitious coordinate system transformation stuff if you want to show that doesn't mean anything. So check this out. Even if they're using a geocentric transformation, right? What they're doing is they're going to the center of the Earth and they're saying, okay, you're in the center of the Earth. And then the actual surface of the Earth is a hollow sphere, and the celestial bodies are fixed on that. They're rotating around you. But one observer only sees that one hemisphere at a time. So right. So when they go and they're not visible anymore, that's either due to them going on, due to the Earth being a ball, or it just being part of that same optical phenomenon we talked about, like a limit of vision. So if something goes so far away that you can't see it, that's our position. And we're saying that the way that it's mapped out, and especially with them using negative coordinates to describe things that are so-called below the horizon, there's no difference in mapping that out and merging it together. It doesn't mean anything.
Okay, so you talk about limited vision, but isn't it true that anybody anywhere on the Earth can always see half the stars, or thereabouts?
Yeah, that's exactly what I said.
Okay,
in,
so
in your field of vision, that's what you see celestially. So the celestial, or what
you perfectly see half of a sphere in your vision.
Yep.
half of the stars. So how would that work on a flat plane? I mean, if I gave you a flat map and then I said, put this dome over it so that the people see half the stars, kind of like in Shane's model, right?
Yeah, it would
But
work
the
exactly
problem
like
is there's a
this.
lot of other Earth there where there's more space there for people to see more than half the stars.
It
On the globe, you can only see half. Are you sharing?
Yeah. Oh, yeah. Sorry, real quick. Yeah, it works It works exactly like this. Right. So you only see. So instead of seeing this out here like this, you see it only projected into your half where you're at.
Right, but I'm saying that is exactly half of the stars in that dome. But then other people all over the rest of the Earth also only see half.
It's latitude dependent and observer centric. It's the same thing as this right here. Check this out. Let's see. So Theo, go over to here. So this is Shane's half projection hemisphere, right? Where Walter Bislin, whoever you want to say, or even the Chinese and Japanese, right? We have this hemisphere of vision. Well, this is the globe. This is the globe variant of it. Same exact situation. Same thing. They're literally identical, and they all require. They're all observer centric. So
Okay.
that's why
one of them makes sense because there's only half the stars are visible for that person on the globe. The other half of the stars are blocked by the globe. So but there's no, the explanation from the flat Earth has to be distance related, that we can't see stars because of their distance, right? Or just it's magic. Because the globe has an actual reason. It actually explains, it actually describes. Whereas the flat Earth is just, believe us, bro, that light works this way. It puts the sun exactly where the globe model calls for it. It just seems to me like what it does. When you go back to Shane's model.
Yeah, listen. When everything arcs across your horizon the same exact way. Everything goes from the top, right here, like at your zenith, and then as it gets further away, it gets lower in the horizon. That's true in both models as an optical phenomenon. It's just when you can't see it, you guys are like, well, that's because the globe is blocking the half. We're just saying that's where the ground meets the sky, and that's as far as you can see.
Okay, so what about when, let's say, circumpolar stars in the south, those go around the pole star, that's their full night's travel, yet the stars on the complete other side of the Earth. Right, the southern stars are the outer edge of the sky dome. Right, the stars are, I mean, I could show you if is that, that's not Shane's model you can play with right now?
So there's two hemispheres of stars.
Right, so is that, okay, so go to that one and push the person out to like latitude 55. 55 south, yeah, so go there. Okay, so let's say there. And then turn on the stars.
I don't know how.
They should be at the top. There's go up there. There's like a button that says stars. And you just like press a button or something that shows up. Stars. There you go. Okay, so now let's get a look at it. Wait, it moved you, huh? Go ahead and go back to where we were a second ago. I don't know why it's moving you. Latitude again, 55 or something. So, okay, so see the red stars at the that go around Sigma Octantis? Yep. Okay, so if you pull the time forward a little bit just so we can see that in a day, those stars just circle. But those are actually the southern stars, which means half the night they're on the other side of the Earth. So if it's distance dependent, then we would be able to see Polaris, because how could we see stars further than Polaris? Because those red stars are not, the southern stars are the outer edge of the stars. There is no stars that stay and circle like they do in the north. So think about the circumpolar stars in the north, on a globe or on a flat Earth, they both work, because the stars never set, because they just stay right above the North Pole star. They stay right around it. They get orbited overnight. Okay, great. Now if we go to the south, the same thing happens in the opposite direction. Yet you're telling me that the stars that we see are just, you said they basically rise and set, everything's the same. Well, it's not the same, because those stars there on this globe are actually there. They actually just circle the South Pole star. Yeah. Whereas on your flat map, we have to pretend now that somehow those just manifest over there.
Yeah, I got you. So okay. This is conflating the two things as like a God's eye view perspective. Nobody sees the full spectrum of the stars like that. It's the latitude.
No, but I was down in the south and I saw the southern pole stars that just go around it.
Yeah, I don't disagree. That's a latitude dependent phenomenon in, like, as you're away from the equator in the south. The same thing happens in the north for the north clouds. Okay.
But the north stars are actually there, right? The north stars are there.
And the southern stars aren't?
No, you just told me that those southern stars that just circle the dome there, you're saying that those are the outer edge of the stars, so they actually travel all the way to the other side of the Earth.
That's not what I said. I said that's a latitude. Seeing them and how you see them is latitude dependent, whether you're north or south of the equator. That's
latitude dependent. Okay, so, of course they're latitude dependent. I mean, what you're saying is that it depends on where you're standing, what we see in the sky. Yeah, no shit.
Right, but then you're turning around and saying that it doesn't matter and we should see Polaris from down here.
So the stars that are in the south are the outer disk of the stars, the outer rim of the stars. That's the southern stars, right? Yeah. Okay, so as the stars go around in one day and do a circle, those are the stars that you see go around Sigma Octantis. The ones that go all the way to the other side of the Earth. So when you see them up right next to the South Pole star, they're really on the other side of the Earth over by Australia, which is further than Polaris. So I don't get how we can say that it's just magically appearing there. I mean, that's why this is a stolen globe projection. Well, it is. I mean, the people in the south. So do you know that that's exactly what you're supposed to see from the south according to the globe? That half hemisphere is exactly what the globe predicts.
Did you know that it's also what a flat Earth predicts with two star fields for a map?
Okay, but it's not what a flat Earth predicts, because a flat Earth tells me that those stars are on the other side of the Earth. That's what the flat Earth predicts. You just moved them. You just said that's what the flat Earth predicts, and then you moved it to where they're supposed to be, and you said, okay, that flat Earth predicted that. No, it didn't. You moved them there.
Only when you're speaking through the God's eye view perspective. If we're talking the ground positions of the stars and what they're physically mapped to, they're separate for a reason. That's why they used to have two separate star fields. Merging the two with the fictitious observer in the center.
Yeah, they had two star fields because there's the north and the southern stars, two different sets of stars.
And that phenomenon can't exist on flat Earth because
the southern stars go away from you all the way to the other side of the Earth, but I still see them in my dome sky. They still stay there, but they're the southern stars. In the north, it makes sense because they are there. The north stars are there. But in the south, if it's the outer disk, then so like play the stars that go around Sigma Octantis. I just don't know if people realize this. Put it go back to right there, and then just play the time of day. Is that day? Okay, so all those stars that are spinning above your head in the south are actually going around the Earth on the outskirts. They're not going around the pole star, or else they're going around the pole star of a globe. Well, so you're saying that the southern stars in your mind are actually staying there and going around the south pole? Because let me explain. If you're over in Australia, you see the same stars circling the same south pole star. So they also have to see the same stars in their sky, and then so it's just everybody on the outskirts of the Earth sees the stars no matter where they're at on the outskirts on the other side.
Yeah,
I mean, it doesn't work. It doesn't work.
I don't know how it doesn't work because the Chinese went and did the exact same thing. They mapped out the southern the exact same way they mapped out the south. What they did is they went to the Falkland Islands, they went to the star Canopus, and they got almost to the zenith. Like, they had it at like 88 degrees under their zenith instead of 90, and then they mapped everything out with latitude dependent effects based off of that. And they used hold on one second. And they used
but just when you're saying latitude dependent, that's of course everything is latitude dependent.
Single observer latitude dependency is key here because you keep.
But that's no matter what. That's no matter what. Who believes differently than that? Who believes it's not latitude dependent?
Because you keep conceptualizing it as a unified total model, and that's not
no, I'm saying,
observer sees.
Talking about what the observer sees. So do me a favor, grab the longitude and move the longitude and watch what happens, and tell me this is just by accident. Do you see that?
Mm-hmm.
So everybody on the outskirts of the Earth sees the pole star completely in an opposite direction. Notice those people see it over there, those people see it over there, but it's the same field of stars. So clearly there's a model that says there's a reason for that. And the reason for that is because you're at the bottom of a globe and you're all looking in the same direction to the South Pole. That's telling us that the South Pole star is in a different direction for everybody. So I mean, it's kind of, now if you move the other way, move the latitude line and watch how it just unfolds perfectly. It's a sphere that unfolds, no, latitude, sorry, that one. If you just kind of watch it roll, that's a sphere. It just works perfectly. That you have the North Pole star, and then as you go out towards the edge, now the South Pole star unrolls, and now we can see that in the sky. So it's just funny that I didn't know that you still think that it's this map. Because if we want to show something else, now go to
what do you think this map is? This map is just the positions of the stars on the vernal equinox. That's all this map ever was, for two separate hemispheres and then merged together mathematically. What these observers are seeing, like, they don't see it all at the same time. They all see it on the same latitude. So
they don't see it at the same time. It's time dependent. Yeah.
What I was saying though is that the Chinese went and mapped all this out as geocentric flat earthers using Canopus and then the southern Sigma Octantis, but there's two stars that lead it because Sigma Octantis isn't bright enough. So they used those two stars.
Wrong.
Hold on. No, they were identical because later on we can get to an eclipse method that they used to come up with how to determine longitude, and it's identical to what's used today, like 1-to-1, like the accuracy. I'm pretty sure that the Jesuits took the Chinese model and then combined it mathematically, retold a whole story about how they needed to get a synchronized clock so that they could tell time at sea. The Chinese already did all of that in the early 1300s.
Can you turn on the paths real quick so we can see them? There's a button, I believe, to turn on the light paths.
Yeah, you want to see some bendy light or whatever?
Yes, I don't remember where you do it. And then, do we see the sun or no? I can't really see the top of that. Where's the sun at right now? I don't know where the sun is. Do you have to turn it on up top or something?
All right, we're on star mode. There's no sun right now.
Okay, you can't. Let's bring the sun back just real quick so I can see. Okay, so that's the sun. Oh, it's kind of doing a video. So on the day that we saw the sun south of us in Antarctica, when it's actually over Australia, is there two suns? Or explain that to me, or what you feel now that you know that there is. You said earlier that you think there's a 24-hour sun. So people in Australia.
Yeah, we all see our own individual sun. All the stars are all individual to us relative to whatever latitude we're at. And I can show you that despite this projection in the globe saying that, well, the reason is that the sun is underneath you and all that because of the converging latitude lines, I can show you that over 7 million meters, the sun doesn't drop in elevation, the sun and the moon. Because like the big takeaway here, like forget about the socio-terrestrial measurements of mountains and stuff for a second, and like just observing the stars and where they're at and making a map based of it and having converging longitude lines and all that. because like all that's going to work out mathematically per the latitude, or I'm sorry, per the hemisphere that it was mapped to. But when we introduce the physical occlusions, like what's blocking out the sun to create a shadow over the ground and create triangles with that per every observer at their location, what I can show you is that the sun and the moon do not change in elevation, so they're always parallel to the ground. That's the most significant thing put forward here, because all we're discussing is how apparent positions were mapped out. And to quote from Copernicus, if you're following what was conceived by astronomers for another purpose, i.e. conceptual models for ease of teaching,
Right.
then you'll leave astronomy a bigger fool than what you're talking, or than when you entered. And what I'm proposing is unique because we're using the so-called light source of the object rather than the apparent position. So based on what the whole model is based on, it's not even based on the apparent positions that we see necessarily. It's based on the time that true position will come back in 24 hours. Because as these things get lower in the horizon, they end up lingering, and they don't follow the 15 degree per hour relationship at that. So everything is actually based off of where the light source is from a zenith measurement taken on the equinox, and then
Earth to inside that viewpoint for that person.
No, we don't have to
You
do. No, we don't have to do that at all. The
Okay,
observer, it's single observer built, man. And then what was the other thing you said, real quick? Oh yeah, about the globe model. There's no globe model, bro. What you're looking at here are latitude and longitude lines.
Hold on a second. What do you mean there's no globe model? Go to Google Earth. That's a globe model.
Okay, and I'm going to explain to you what that's representing, right?
Okay.
That's put together from latitude and longitude lines. Latitude and longitude lines are just positions of where stars transited.
But they exist on a globe. That's where they were drawn.
You're saying that they exist on a globe, but you can't know that just from the apparent position alone, just from mapping them off of a cyclical nature, just by mapping their apparent position. And when they come back, that doesn't tell you anything unique. That could go either way. And then
there's a model that calls for that, and there's a model that needs a lot of help to get that.
These are the same thing. This isn't a model. This is a latitude and longitude coordinate system, bro.
Okay, so go to 70 degrees, go to 80 degrees south, and like minus 120 east or west, just so we can get kind of where Union Glacier is. Is it working there? I could bring it up too. I wanted that little dome on there. I don't know why the dome disappeared.
Yeah,
I'll
sure.
select it right here.
I'm not sure why it's back there. Give me a second. Let me refresh. Yeah, it's back. It's back. I got you.
Okay. So yes, thank you. Let me go in here. I can get back to the screen. I lost it. Where are you? Okay. So and then so where are you at? I think you went 90 degrees. So go to 80 degrees just so we can get off the South Pole there. No, I'm sorry. Latitude 80. What does that do? Okay, I guess you're okay. I can see it moving. All right, so there, and then put the sun or put the date where it says day of the year. Put it like 3:55. One of those says day of the year. Do you see it? Like maybe go 3:55-ish. Okay, and then there's sun. All right, so now put the sun at where it's off on top of Australia. Oh, I see. You're at the bottom of South Africa. Sorry, can you do the longitude? Move that for me just to Union Glacier, which is going to be like take it the other way. No, the other way. There you go. Right around there. Back about 120. There. Good. Okay, so now take the sun over to where it's above Australia, which would be time of day. Is it there? Okay, so now the people in Australia see the sun above their head, and they're getting heat. It's heating them. And then the people in Union Glacier see the sun on the opposite wall. So there's two suns. You're saying there's not two suns, or there is two suns? You're saying everybody has their own sun? There's infinite suns?
Everyone sees their own individual sun that's latitude dependent. So what you're looking at is how you're going to perceive it in the southern hemisphere. It's going to do an Antarc for you as the true position of the sun circles above us parallel to the ground, as noted by the eclipse data that we'll get to.
Okay. So let's say it is parallel to the ground. That's fine. But I'm saying it's way over there. It's 30,000 miles behind me, but it just appears on that wall.
Oh, no, that's not fine. It refutes curvature conclusively, because there would be 4 million miles of curvature to that 7 million mile distance based off of an elevation of the sun being 6,731 meters high.
Wait, what?
Yeah. Well, we haven't got to the.
But you're saying something moves parallel, but you mean it's moving level?
It's moving parallel to the ground. Yes.
That's called level.
Sure, level to the ground.
Yeah. So that's a curved path.
What?
You understand the definition of level?
Nah, dude.
Okay, well, so level and horizontal now are the same word. So we can just replace one word with the other. They don't mean anything different.
So listen, when I say they're parallel to the ground,
I'm asking. I asked a question. Okay, but I asked a question. Can we just call level things horizontal now and horizontal level? They're the same word? Because you just laughed because I said they're different.
Horizontal, straight, and level. Level doesn't mean curve. Level meaning curve is like redefined so that they could talk about.
So then you're saying that there's two words.
Orthographic projections of an ellipsoid model and all that stuff.
No, it's just the definition of level. Level is from a certain point. So if you're saying level from the center of the Earth, then the oceans are level on a globe. That's how it works. You can laugh at it, but that's how it works. You have to admit that's how they say it works.
That is exactly how they defined it. Well, what I'm talking about here, right? So do you understand that if stellarium is a globe tool and all this stuff and all this globe stuff, that the elevations, the true positions have to actually change in elevation because the contour of the Earth is, we'll take the rotation example, right? The elevation change is physically being created because the curvature of Earth, right? So the physical, so the true position of the star would also have to change as well. That's what the whole model is predicated on. And when they say that when you're just standing, when there's an observer standing here and that star is setting into the horizon, they're saying that its true position, its true elevation is now at 1 degree. Now it's sub 1 degree. Now it's negative coordinates. Now it's under the ball, right? What I'm showing you, what I can show you is that during an eclipse over the course of 7 million meters, where there should be 4 million meters of curvature, there is none. There's a 10,000 meter deviation. That's it.
Oh, you have to show that. I have no idea I don't even know how far 10,000 meters is. 30,000 feet?
10,000 meter would be
6 miles?
10,000 meters is like 1,000 kilometers. So whatever 1,000 kilometers is in miles.
Oh, 10,000 meters, sorry.
Yeah.
So wait, that's 30,000 feet. 30,000 feet, 6 miles.
Sorry, did I say 6 million meters or did I say 600,000?
I don't know. I mean, I got very confused.
It's
meters.
6 million meters comes out to
6 million. It seems a little high, though.
Well, no. Well, so in kilometers, though, that's just 6,000. So whatever the conversion is from thousands of kilometers to miles is what you would.
Okay. I don't even give it what we're talking about there. I don't know how the eclipse has something to do with this model.
Because that. Well, it has to do with all models that use the latitude and longitude dependent, especially those in particular that say that the reason that the stars aren't visible is because the globe is blocking them because the physical elevation is changing. That's
so where I'm confused is if, let's say I'm in California and I say that the sun is a certain distance above my head. And then hours later, when it's above the head of somebody in wherever, Hawaii, it would be the same distance above their head. So I could see where you're just drawing that and saying, well, look, it's a level, it's the flat line. It's flat the whole way. But yeah, because it's staying level, it's the same distance from the Earth, no matter where it's at. I mean, not at the same time when it gets above their head versus above my head.
Exactly. And we could plot out the whole thing and show that at no time is it ever going under anyone's head at any angle. That's the.
Well, we see from a plane, you can see the sun below your eye line.
When we get to, do you just want to watch the video real quick so we can, because this
is,
you're getting half of the argument is not doing any.
Okay. Yeah, I'll watch this video you want to watch and we'll.
All right. Thank you.
Go from there.
All right.
No, but I think it's a lot simpler than what we are talking about. But go ahead. Yeah, I'll watch this.
Yeah, go ahead. Thank you. I appreciate it. All right. So I got it playing at 1.5 speed. So it's pretty normal speaking tone. It's not too fast. Now that'll reduce the time to 13 minutes and 30 seconds. So we don't have to do the full 19.
Okay. Tell everybody what we're watching though so that we can.
Okay. Yep. Okay. So what we're about to watch is a brief recap in the celestial theodolite and what we mean when the true elevation of the star is traveling parallel to the ground and it's not actually deviating like it should as per the globe requirements. So Brian gives a nice little recap on that and what the triangle situation is. And then what he's going to do is he's going to independently derive the altitude of the moon using the total length of the shadow produced during an eclipse. And then from that, he's going to derive the altitude of the sun based off of the occlusion from that. And then we're going to plot that out over all the observers for the 7 million meters that the shadow length was as the eclipse occurred. So as the eclipse occurs, we can, they should be changing in elevation. And what we're going to see is none. And he's going to go through how he did all of that and break it down. It's just pretty simple trig functions. And then if you have any questions during it, you can pause it or just tell me when to pause and I can answer them.
So just is your position though that we can tell the shape of the ground with lights in the sky or we cannot? Because you've heard other flat earthers.
Yeah. So just watching the apparent position alone, nothing unique can be said. When you introduce occlusions, when you introduce terrestrial features like a mountain peak of a known elevation, you can start to make some determinations because on a globe, the elevation of the mountain is going to be physically lower, which results in a different angle. And the whole system is derived from combining what we see with central angle theorem. So in other words, like when how you sometimes give the example of like, oh well, the Earth's so big that it just like Home Depot type stuff and the curvature and whatnot. Well, that's actually not true because if at the distances that we're using for the cell Theo, what we found is that the description of how the stars move in the sky relative to an observer follows the full, like what we call the full celestial drop, which I'll show you some diagrams here in a second for the angles and all that. But half of that angle is what they call drop over distance, and it's always half. So in order for that to be true, there can't be. This mountain can't also be a flat Earth prediction. You know what I mean? Like there's mandatorily going to be a different angle produced out of this because the half of the curvature, the other half of it, if you double it, tells you where the star's at. That can't be true if it doesn't work that way. So the rationale of like, well, it's just a Home Depot situation is not true. There's absolutely a mathematical difference between the two, and especially because angles equal time in celestial navigation, the difference in angles is equal to time.
You think that this actually is going to overtake things like the North Pole star moving 1 degree per 69 miles, something that's so simple that anybody can do, that anybody can verify, that everybody can prove for themselves? You think this method is going to overtake those things, or what? Because I don't see how you can think that the flat Earth is the truth. Unless it's going to answer questions, it should be like things should be getting better because the flat Earth is coming out, right? Like if we should be improving on the globe's nonsense, and we should say, no, the globe is nonsense. So the flat Earth, now that we know the Earth's flat, here's how we're going to repair and fix things that are a problem. But the globe Earth it answers all questions. Just by saying sphere, it answers the upside down moon, the upside down sun, the backwards moving sun and backwards moving moon, and the backwards setting right to left in the south and left to right in the north. Everything is answered one simple word, sphere. However, in this world, it's way more convoluted. Everything you just said right now is more confusing than I've ever heard anything on the globe. Ever.
Well, that's because you have a gross misunderstanding of the globe.
Well,
That's not
how's it
that's
close if I
not
say we
that,
can
that's
place
not
two
my fault,
people?
dude. Your example was how is this going to take over 69 miles per degree? Like not even differentiating that we're talking a difference in true position versus apparent
No,
position, and that we
nothing.
see
I'm saying,
and that we see the same thing. So like
well, there's
how
simple explanations. There's simple understandings when it comes to the globe. Example being that anybody can right now take their angle to Polaris, figure it out, okay, whatever that is, then drive 69 miles north, and the North Star will pop up by 1 degree. So you do that
you
over
can
and
do
over
that
again.
you could do that on flat Earth too, dog. It's the same. Like I don't like your
What do you mean?
examples
What?
means nothing
How could you do that on a flat Earth?
because we see in the same hemisphere of vision that the globe is using mapped as a sphere of a terrestrial sphere.
So it just happens to match then the 24901 globe.
Yep.
Okay, well, hold on a second. Now, on a globe Earth, what is the circumference of the equator? 24901, right? Or thereabouts. Okay, on a flat Earth, what is the distance of an equator?
Same exact distance. It's the same exact thing.
That's impossible. It's impossible.
I know. And when you do the triangle thing and multiply it out.
No triangle. What's the difference? What's the distance between the North Pole? What's the distance between the North Pole and the equator?
Show me the mean that you're talking about. It's the same as the radius of Earth.
There's no meme. I'm asking you what. Okay, North Pole to equator on the globe, I'll tell you, is 6,250 miles, 6,250.
Same exact distance.
Okay, then if it's the same exact distance, then that's the radius of a circle, and the radius of a circle at 2 pi r comes out to then the radius. Then it comes out to 39,000 miles. So the equator on the flat Earth is 39,000, not 24,901.
Yep.
So there's no way that your 1 degree per mile would work because on the globe, that's 360 times 69 miles is exactly 24,901.
Yeah, that's a misapplication of the math, and I'll get the proper response for that here in a second.
Okay.
So we will definitely come back to that. Not running from it. I don't have the thing to address it, but I know exactly what you're talking about. That's why I said, because I've seen it in meme form, but it's not exactly correct. So we'll get to that. We'll get to that while or I'll look for that while we play this video. But so to reiterate, like this is the difference in true position versus apparent, and this is why I'm saying this is why my position is that we all see our own individual lights relative to us in our own dome of vision, because what we're going to see here is that the elevation change that's required as per the physicality given to us through the model presented as the globe doesn't actually occur as it should. So here we go.
Okay. Yes, and you'll press play. Go ahead.
Hello,
I don't hear
this
sound.
is Llamazing, and I'm going to present a new application for the celestial theodolite today. But first, let's recap what it is for those who don't know.
No. Did you hit with share? Share with sound?
Oh, 1 second. Let me try again.
Yep. And then what I'll tell everybody is after this video is done, I will look at super chats and answer those first batch, and then we'll go back to talking. So this way you don't have to wait till the very end. So just in 13 minutes, we'll go over those. What happened to me?
I reshared it to see if I could get the audio to work. You're good. Let me know if you hear it.
The celestial theodolite uses observations of stars setting behind mountain peaks.
We hear nothing.
Second, where the star.
What do you have that playing on? Can you send it to me on Telegram? I'll play it over here.
Yeah, I certainly can. Let me send you the YouTube link.
And it might be the same thing that you can't hear, but I'm sure you've heard it before. Okay, send me YouTube?
Yeah. All right, here you go. When you screen share it, I'll be able to hear the audio and stuff play through. So just play it through, and we'll just watch it on through you vicariously or whatever.
Okay. Let me find where you're at here. Red Ellen, YouTube. Come over there. Can you hear that? Did you hear that one or no? You didn't hear that one? Okay. Well, you said you heard the sound, so we'll be fine. It's just everybody can hear it. And you said put it at 1.5 speed. Is that correct? Is that what you said?
Yeah. Sorry. Yeah. Just play it at 1.5, and then let me know when you hit play, and I'll hit play on my end so we can watch that.
Let me get this. We're just looking at that. Trying to see what this is on the whole screen. Okay. I see what's going on. Okay. Let me put this over here. Sorry, we got to fix this for you. I think that's the whole video. What is this thing over here? Calculate sun height. Okay, that's from the video. Okay.
Hello, this is Llamazing, and I'm going to present a new application for the celestial theodolite today. But first, let's recap what it is for those who don't know. The celestial theodolite uses observations of stars setting behind mountain peaks. By noting the exact second where the star was no longer visible, you can then consult an astronomical almanac to determine the uncorrected angle to the star at the time, as in not influenced by refractive and other optical effects. By forming a right triangle at the base of the observed mountain with the other 2 points at the observer and the mountain peak, the geometric angle to the mountain can be easily calculated using basic trigonometry, where the angle is the arctangent of the height of the peak minus the height of the observer for this vertical distance divided by the ground distance, which is also going to be equal to the angle to the star from the almanac. It is interesting that the physical angle to the peak of the mountain comes out the same as the almanac angle to the star, despite there being no allowance for Earth curvature in the calculations. Most of the observations are done at long enough distances away that the amount of ground curvature would be significant. When the calculations are done using globe math, and that accounts for the curvature, the numbers are off by the amount of ground curvature present. Refraction, the bending of light due to the changing density of the atmosphere, has to be invoked to compensate for that difference, bringing it back to where it would be without the curvature. The following celestial theodolite measurements have been made to date, sorted by observation distance. The farthest one done so far has been to North Peak in Colorado, with a distance of 130,000 meters. But instead of discussing stars getting included behind mountain peaks today, let's try something new and completely shatter the current longest distance observation, which is going to be 7.7 million meters, which is 60 times the furthest record to date. And here's what we're discussing: solar eclipses. A total solar eclipse occurred on April 8th, 2024 in the United States, with totality lasting from 4:30 p.m. to 8 p.m. UTC time, and that was 4.5 minutes at any one given location. Noteworthy cities along the path are Austin, Texas, Dallas, Texas, Little Rock, Arkansas, Indianapolis, Indiana, Toledo, Ohio, and Rochester, New York. The path was going from the southwest to the northeast. And then, of course, the sun and moon are traveling from the east to the west. And the reason that the eclipse path travels from west to east is because the sun outpaces the moon, swinging the shadow around as it passes. The reason the path of the eclipse travels north is because the sun is getting farther away from the moon, making the angle of the shadow down to the ground more shallow and thus farther reaching. So now we've got to understand the eclipse. Where to begin? First, I want to understand why the path of the eclipse shadow would travel to the north. So the first thing to do is study the movement of the sun and moon in stellarium, which is a planetary map showing the position of the stars for a given location and time. Starting at the farthest point for the eclipse shadow, I drew a great circle route to the moon. Then at intervals of 1 nautical mile, which is 1/60th of a degree of longitude, I used Python to calculate the latitude and longitude coordinates for each of those interval points. I also recorded the observer's altitude angle to the sun and moon, which excludes refractive effects. And then I applied the angle versus ground distance for both the sun and the moon. So starting here with the sun. The first step is to create a linear trend line of the plotted data, which you can see is this dashed blue line. And the R value is high, indicating it's a good match, or close to one rather. The slope of the trend line gives rise over run, so the slope value of -9 e to the -6 has units of degrees per meter. Vertical is degrees, and the horizontal is millions of meters. When we take the inverse, 111,000 meters per degree, and then divide by 1852, which gives us 60.028 nautical miles per degree. This is close to the expected 60 nautical miles per degree, where the sun drops by 1 degree for every 1 degree of distance traveled. Going back to this 111,000 meters per degree number, if we multiply by 360 degrees to get the circumference, and then divide by 2 pi, we get the radius value of 6.3 million meters. This is close to the 6371 radius for the Earth value, which is what we expect. But now when we go to the moon, something interesting happens. If we generate the trend line like before, this gives us 9.13 e to the -6 degrees per meter. We're to get 109,000, and then when we divide by 1852, we get -59.1327 nautical miles per degree. Most unexpected. And then when you continue the math out, that results in a smaller radius value of 6.27 million meters. So putting this into perspective, when starting with the sun directly overhead and traveling 5,400 nautical miles, or 90 degrees longitude, the sun drops down to 0 degrees. For the moon, however, we only have to travel 5,300 nautical miles, which equates to 88.7 degrees longitude, for the moon to drop down to 0 degrees. Putting it another way, if we see the sun as if it is traveling along a celestial sphere with the radius of the Earth, then we see the moon traveling along a slightly smaller celestial sphere. And that's what we're showing here with a side view of where the sun and moon appear as the observer increases the ground distance. So the scale is millions of meters in both directions. And with the sun, it's at 6.3 million meters, the moon 6.27. And then if we multiply by pi over 2, we get the base radius, which is 10 million meters to the sun and 9.8 million meters to the moon. So now that we have that background out of the way, we can actually analyze the data. And you can see here the path of the center of totality spanning across the US. And the data for the eclipse path is available as a Google Earth KML file from this NASA website. It tells us precisely where the center of the eclipse shadow is cast at a given time. There are 6,770 data points at 1-second intervals spanning from 6 p.m. to 7:45 p.m. for 112 total minutes. Next, the latitude and longitude coordinates for the ground positions of the sun and moon are needed over that time span. I wrote a Python script to extract this information using the AstroPy module. This allows us to calculate the distance along the ground from the observer at the eclipse shadow to both the sun and moon positions, giving us a base distance of our triangle. I also extracted the altitude measured in degrees of the sun and moon above the horizon for the observer, but these are for reference only. They represent an optical position in the sky, and we need to use the true physical position. The final measurement needed is the height of the object doing the including, which in this case is the height of the moon. What we're going to do is assume the moon is fixed at the 6.27 million meter height we found earlier, and assume it's only an optical effect that causes the apparent position of the moon to drop in the sky as we get farther and farther away from it. The following table summarizes the known and unknown parameters. So first we have center of the eclipse shadow, latitude and longitude, which we got from the data file from NASA. Then comes the observer elevation height, where we can take those lat long coordinates and upload them to gpsvisualizer.com, which will export a CSV with the elevation data. Then the sun and moon ground position, latitude and longitude, which is generated in Python. We have the ground distance from observer to sun and moon, which is calculated using Haversine from those latitude and longitude coordinates. The height of the sun and moon is what we looked at earlier, and we're going to assume a fixed height over the observation period of 112 minutes. There's the observer angle to the sun and moon, which is generated in Python, but we're not going to use it because it is the apparent position. And then finally, the physical occluded angle from observer to sun and moon, which we don't know, but we can solve using basic trigonometry. Our assumptions are as follows. Number one, the sun and moon are at different fixed heights as they travel east to west. We'll consider any change in height negligible over the 112-minute observation window. Number two, assume the physical positions of the sun and moon are in direct alignment with the position of the observer. That is, drawing a straight line from the observer to the physical location of the sun is going to intersect the physical location of the moon. Third, the light from the sun to the moon, and likewise the shadow from the moon to the observer, is going to follow a straight path, where refractive effects of the light are negligible. Since we're using physical and not optical positions for the sun and moon, optical effects do not apply. And lastly, no corrections are going to be accounted for ground curvature. And here are the objectives of the analysis. Celestial theodolite calculations generally involve calculating the height of the mountain peak using a triangle of the physical geometry and then comparing to the known height in order to evaluate the measure of success. Lacking certain key measurement values forces a different tactic for this analysis. In this case, over 6,000 data points are available to analyze, so instead, success will be measured in regard to consistency across the full dataset.
Can you pause real quick? I want to check next question.
Yep.
Oh, all right. Just real quick. So how did you figure out the heights of the sun and moon?
Good question. So doing rise over run using the length of the shadow and then the angle that we have for the observer viewing the moon.
And you came up with 10 million meters?
Yep, the height of the celestial sphere, which is
62 something in miles?
Yep, comes out to be the same ratio as if you did 1/10 millionth of a terrestrial meridian or whatever. Like, so what that comes out, what that basically means is 6218 would be the if you did it in nautical miles, I think it is what it comes out to. So it all comes out to be the same thing. So like earlier when I was talking about how
Okay, but if it's all the same thing, then don't we need to have the distance between the North Pole and the equator be 6250?
Yes.
Okay, that's what it is on the globe.
That's
but what
Yeah, dude,
Be honest.
the globe is just constructed from a symmetrical coordinate system with the positions of the stars.
Okay, but
So
you know how a
that's
circle works. So let's not play dumb.
I
You know how a
do.
circle works. Hold on, let me just make sure because you're making it sound like this is more difficult than it is. We know how a circle is, and we know how to get the circumference and the radius and everything from a circle. So if you think of the equator as a circle, the equator is a big circle. Okay, great. And the radius is going to be from the North Pole to that circle. So the radius of the flat Earth is 6250. So when you do 2 pi r, which is 6.28 times 6.28 times the 2 pi r's radius. Okay, so it's 6.28 times the 6250. Let me see what we get here. Make sure I'm seeing this right. So if we go 6250 times 6.28, which is going to be the 2
comes out
pi.
to
Right. So that's the
39,450.
equator.
Yeah,
That's the equator distance.
yeah, that's because you're looking at a flattened out graticule and doing that. What I'm saying is that if you take out the latitude lines and multiply them out from the equator to the North Pole, it comes out to be 6210. You do the same thing for the south, it comes out to be the exact same thing. It's a symmetrical,
Right.
it's a symmetrical coordinate system.
Or we live on a symmetrical land.
Yeah, well, if that were true, then there would be 4 million meters of deviation in the true positions of the sun and moon as this eclipse happens. Let's see what happens.
Wait, there'd be 4 meters in the difference of what?
There would be 4 million meters of change in elevation if what you're proposing about the ground being a globe is true. If it's not, then what's going to happen is these are going to travel parallel to the ground with no change.
Okay, but if somebody walked, then if that is the distance between the circumference of that circle is 39,250.
Jeran, we can it's calculated observer individual through the whole string. It never changes deviation based on the angle. It's always the same altitude. It makes congruent triangles, bro.
I don't know what you're saying.
Well,
But I'm saying something very simple. Anybody knows how to do the figure out a circle.
I get what you're saying, but also, right, there's going to be elevation change for these people. Regardless, these observers over the distance are going to start to show an elevation change when we calculate it out. The only way that wouldn't be the case is if they were just parallel to the sky the whole time.
All right, let's continue the video. You
Because
gonna
like,
get to that again?
he's setting the stage for how he's deriving everything. Because like to answer the question, like how do you derive the altitude of the moon and the sun? Well, once we have the moon's altitude from the shadow length and the angle from the observers, what we can do is because the occlusion happens, we can derive what it would be for the sun under the same thing, making a congruent triangle. So as he's about to get to that to the juicy part here, he just had to lay the foundational groundwork.
Okay.
But can we consistently calculate the same height across all the
Press play whenever you're ready, sir.
I want to see what somebody wrote here. It says Jeran, pi needs to be 2 for a 24,901 mile equator and a 6210 rate. Okay, so yeah, I mean pi's not 2. So all right, here we go.
data points? These 6,000 data points aren't simply a similar measurement taken over and over again. Since the sun and moon are moving in the opposite direction as eclipse shadow, the distance is constantly increasing from 2.6 million meters to 7.7 million meters, which is an increase by a factor of 3. Likewise, the altitude angle from the observer to the moon drastically changes as well, going from 70 degrees down to 19 degrees, a change of 51 degrees. And then the azimuth to the moon sweeps out 140 degrees, the observer latitude changes 30 degrees, and the observer longitude changes 60 degrees. The observer elevation is fairly consistent except for this mountain range over Mexico. So the key parameters vary quite a bit over the dataset. Now let's get into the actual analysis. The first step is we're going to assume the height of the moon is fixed at the 6.27 million meters number we found in section 2. H moon equals 6.274 million meters. Step 2, calculate the occlusion angle using a right triangle where the base is equal to the ground distance from the observer to the moon and where the height is the moon height. So the occlusion angle becomes the arctangent of the height of the moon divided by the distance. Step 3, we're going to make another right triangle from the observer to the sun using the same occlusion angle from step 2. And since in a solar eclipse, the sun and moon are lined up with each other.
Just real quick, I just want to make sure. Is he going to cover then?
Is the same.
It seems to me that if we now know the height of the sun and the height of the moon away from the Earth, then we can figure out whether or not it's supposed to change in angular size, right? So, like for instance,
bro, apparent thing that we all see individually. It's like what we see is not going to follow the rules of like a physical object moving away from you. That's nothing to do with this. You're kind of deviating from the significance of the fact that there should be a physical elevation change if the Earth is a ball, but there's not.
Well, I just want to make sure that I know what. So we have to pretend that the sun and moon are not physical, that they are magical, but everything else that we see on the Earth, a truck, a car, a building, those are real items.
Exactly. Just like you have to believe that they're imaginarily changing physical elevation. Yeah, exact same. Go ahead and press play. Continue.
Same as the angle from the observer to the sun. So now we're solving for the height of the sun, where our equation is height of the sun equals distance of the sun times tangent of that occlusion angle. And that's all there is to it. So now we just have to perform this calculation for all 6,700 data points, and then calculate average and standard deviation values. The average comes out to 6,374,000 meters, which is very close to the 6,371,000 for the Earth's radius. And then the standard deviation comes out to 6,200 meters, which is less than 0.1% of the average, which indicates the data is highly consistent. This is showing the height of the sun plotted out for all 6,000 data points, and the result is very flat. This is versus time. We can also show it versus distance. And the key point to consider here is we're actually starting the eclipse here, and the distance gets smaller and then gets bigger, so it's actually going over itself exactly, and it's so perfect you can't see it. So if you're thinking the reason it looks so flat is because the amount of globe curvature at the scale is negligible, then let's take a look. It most definitely is significant, which you can see here is 4 million meters at the end, which would be very significant compared to the 6 million meters of the sun height. And since we didn't have to account for it in the calculations, that is very telling. And then lastly, let's look at the physical angle versus apparent angle. There's a discrepancy between the physical angle that we calculated and the observed angle given by stellarium, even when it does not include refraction corrections. This disparity is shown below, which increases the lower the angle gets, similar to what we saw with the profiles of the celestial sphere. The sun and moon appear to be lower than their true physical position on account of optical influences. Here we can see the physical location of the moon is at 40 degrees, but the apparent is at 20. So there's a pretty big disparity there. And here's a spreadsheet showing the data. You've got the eclipse path, the sun, latitude, longitude, and distance calculations. Same for the moon. And then here's where I calculated the sun height. So you can see there's just a lot of data points here. And then you've got the average and standard deviation. So in conclusion, the relationship between the sun and moon during the total solar eclipse can be modeled out with very basic trigonometry while maintaining good consistency for the duration of the event. It is not necessary to make any corrections for ground curvature, nor to correct for refractive events, diverting the path of the sun's light. This study does demonstrate that there is a difference in the physical position of where the sun and moon actually are located versus the apparent position where we think that we are seeing them due to optical effects. Even the globe model agrees on this point. This raises the question, is the ground beneath our feet curving, or is it the sky that appears to curve due to the nature of how our eyes perceive it? Notably with the same radius value at which the Earth supposedly curves. I leave it as an exercise to the viewer to draw their own conclusions, but this only scratches the surface, and there's so much more to explore. And then let's briefly go over some things I have here in the appendix. So if you're wondering about moon height over time, here it is mapped out for 2 months. With the eclipse happening here at April 8th.
Said about one part of that. Something about the same radius or something. Let me read that again.
Oh, yeah. So that 6218 value that we were talking about earlier, you derived that same thing off of the altitude of the moon and sun, the constancy of it. Anyway.
6218, right. So he's saying that is the same. Should I read that part again? Where do you say right? Okay. So it's how our eyes perceive it, notably with the same radius value at which the Earth supposedly curves. But the radius value of the Earth curving is 3959, not 6250.
Oh, that's in miles in what he's talking about is in kilometers. It's the same value, and then one might be in nautical miles versus statute miles, but what we're talking about is the exact same thing. It's identical.
Oh, so confusing. So you're talking about the 6250 he's been talking about the whole time is kilometers,
yes,
not miles.
Yes, which comes out to 3959 for miles.
Okay.
All right, we've been doing everything in meters. Do we completely abandon the? Anyway.
Don't do that. It's the only thing I know.
Yeah, it's a rough transition, but yeah. Anyway, whenever you're ready to continue.
Yep.
Here in the appendix. So if you're wondering about moon height over time, here it is mapped out for 2 months, with the eclipse happening here at April 8th, and it is changing by about 10,000 meters over that duration. If we zoom into the period of the actual eclipse, you can see it's going from 535 to 570, so it's less than 40 meters change, so not very significant. And when I plug numbers in with the varying moon height, the average number for the sun height only decreases by 1 meter, and the standard deviation decreases by 10 meters, so it's not that significant of a change. And then earlier we were talking about the 88.7 degree longitude change.
Oh, pause for a second.
Overhead to drop down to 0 degrees. So here we have an observer directly under the moon.
Oh, yeah, I misspoke. This is in miles. It's 6210 miles and then 3959 miles for radius. My bad.
But it said at the same rate that the Earth is curving.
Yes.
So the Earth curves at
radius. So let me. I sent you a GIF to look at that has like the math equivalent for what we're talking about for that.
Oh, on Telegram.
Yeah.
Okay. I'll press that.
Yep. All right. Sorry about that.
At point A, and then at point B is that 88.7 degree longitude difference, showing what it would look like on the globe model. And since we have a right triangle here at point B, it's just a matter of taking the cosine of the adjacent divided by the hypotenuse. So you can see the math here, and it comes out to 275 million meters. Now we're told that the moon is 350 to 400 million meters here in this range, and what we're getting falls a bit short. And then lastly, you might be wondering how you can solve this same process on the globe, where you're solving for the sun height. And it's very similar, but you have different triangles. And then in this case, you're actually accounting for the Earth curvature. But the problem occurs when you have any triangle, the sum of its 3 sides has to equal 180 degrees exactly. And so if I assume the minimum distance to the moon of 350 million meters, what happens is that this distance to the sun angle and the observer angle, those two alone add up to more than 180 degrees, so it's not possible to make a valid triangle, and it doesn't work.
All right, so what happened there in the analysis was the difference between what stellarium shows in regards to how the sun and moon and the celestial bodies, follow that 69 mile per degree relationship. For the sun, it comes out to be like, so if you were standing at the equator at 0 degrees and you were looking out at the sun being at like 89 degrees, it would almost be like, right at the horizon, right? And then the moon would be like 88 point something degrees. And when you trig everything out, you get a distance based off of that, like a physical elevation for it. And what he's saying here is that the distance that he derives using, the stellarium and the occlusions, which is what the globe is supposed to be predicated on. And when you compare that to what they say the actual distance is for, for Kepler's laws in Newtonian dynamics, which is you can derive Newtonian from Kepler and vice versa, so they have to give the same physical distance. He's saying that those distances don't match up to make the congruent triangle to have the eclipse happen the way that we see it. It would be off by a little bit. Now, it's possible that they could introduce like refraction to like correct that or whatever a little bit, I suppose. But what he just pointed out there was the difference between the plane trig using celestial navigation tools versus comparing it to the physical distance that they know that the moon is because of Kepler's laws and Newtonian dynamics and all that.
Okay. And I'll just show what I was talking about real quick so we can move past that. So what I'm saying, and then I guess we'll read the super chats after, but I'm just pointing out that this here is a, let's go with a little bigger this one.
Here's an easy one for you. I sent it to you on Telegram. Okay. You can see it. It's got all the math on it already.
Well, so here's the equator, right? And on a globe, we know that that's 24,901. But on this flat Earth, if we put it on a flat Earth, well, now the radius of that is 6,250, right? So, oops, sorry, it shouldn't be. Where's my dash? Turn that off. Okay, so that's 6,250. So then we can do the math on it. It comes out to 39,000. So I'm just saying that that's a problem because we can do. We know what the Great Circle route is all around the Earth, meaning any place that you're at, it's 24,901 miles to get back to where you are. So you can go north because that's where our longitude lines are, which makes more sense to use those. So if you went north and south, then for every 69 miles, the sun, or that we can use the pole stars, are going to move up by 1 degree. So then how could that be the same on a flat Earth if the distance is different? Clearly, going from the equator to the North Pole on a globe would be 6,250, right?
Yeah, so the answer to your question is you have to know what the tool that you're looking at is representing. When the Gleason's map is flattening out curved lines, they make them straight. That's it's still representing the same thing. Like, it's still representing the same symmetrical things when it's outside of the equator as well. That's why what I'm saying, that it's based on two hemispheres of vision merged together. Okay. So let's talk. So when you multiply out those lines, it comes out to be the same thing on both sides. It's symmetrical. You say it's because of a globe. I say it's because of a symmetrical coordinate system.
Okay, so tell me then let's go to the ground. Let's go to the ground and get out of the sky. So if we go to the ground with, I'm bringing up Google Earth here. Sorry, it's just gonna take me a second. I don't know why I blocked you. I'm gonna bring it over here. So if we look at lines of longitude in the south, so let's go. So isn't this the AE map, the azimuthal equidistant, is everything's equal distant from the North Pole, right? So if we were to take this here and go down to, say, Punta Arenas at 53 degrees south, is that not the distance on the flat Earth as well?
Same exact distance. It's referencing the same exact longitude system.
Gotcha. Okay, so we're going to save that. So that's 9,000, just so we know, 9,837 miles. Okay, so we just drew that line there. We're going to hit save. All right, so now we got that. Now, if we take, again, what the radius of that circle is, which would be, again, 6.28 times that number, what I said here, which was 9,837. So times 9,837 equals 61,776. Okay, so we can divide that by 360 to get the amount of miles per degree. So when we do that, it comes out to 171. Okay, now let's go down here and actually measure it and see what it is on the Earth, because 171 would be a flat Earth result. So let's go down here and see what we get. So we're now measuring a distance between 1 degree of longitude. Let me see if I can see them. So there's 70 point. Let me get it down to where it's easier to see them. So there's 71.3 to 70.3, right? So we're going 71 to 70, and that distance is 40 miles. So the flat Earth predicts 171 miles. The globe Earth predicts 40. And what do you want to bet if we go down there and measure it? What do you think we'll get?
You'll get the symmetrical value for the coordinate system of which it's using. Like, you're again doing it incorrectly and then concluding that the distance would be different when you're using.
Wait, how am I doing it incorrectly?
The same thing, because the method of determining the distance from any southern point on the North Pole to using 2 pi to get the miles per degree, it just makes huge circles. And to determine the distance on a flat Earth, that's what you guys think. That's how you guys think it works.
This is all I did was I figured out what the circle is. I'm sorry, this is not a circle.
We're using the same coordinate system. It literally can't be different. It's referencing the stars.
It literally can, because one of them reconvene on the globe. The lines of longitude get back together at the South Pole. So what do you mean that wouldn't be different? This one here shows the lines of longitude go to the very outskirts and keep expanding. On the globe Earth, they converge. They're very different. And so, yeah, in the north where we all live, it actually makes the flat Earth make sense. That's why going to the south changed my mind. That's why going to the south should change everybody's mind. If anybody goes down there and watches the damn sunset, you're going to realize, oops, this map cannot be right at all. It's so wrong, it's ridiculous. And one of those examples is we just went to 53 degrees south here, and we calculated the distance of this circle. And then we divided by 360, which is how you get the degrees per degree. And it's 4 times off. That means that as a plane left here, if a plane left here and went to fly across this ocean, it's going to have to go 4 times further than the globe says.
Bro, respectfully, that's a misrepresentation of how to use this coordinate system. You don't even draw straight lines.
Oh, so this is not a map.
A curve on that map is the same is the same length in the south as it is in the north, although it visually looks bigger because it's projected out.
That's impossible.
It's literally, bro, it's math. It's the same exact thing.
Hold on a second. So if 2 people are standing next to each other near the South Pole, they would be next to each other. According to this map, you would have one person here and one person here, and they would be next to each other. Those 2 people are standing next to each other. So is this person standing next to them. This person standing, they're next to each other. They can hold hands. They can hold hands, dude. Wake up.
No way. Are they referencing the same coordinate system that's derived from single observer observations?
Hold on a second. If these people standing out here can hold hands.
It's not going to be a different number.
Hold on.
Are there other people out there holding hands?
Dude, If the people out here are holding hands, this is where they would stand, and they're holding hands.
Are there people
So
out there holding hands?
that's if people stood around the South Pole and held hands, that's what they would do. That's where you would plot them.
So listen,
So I'm confused real quick. Is you saying this is a map or not a map?
I'm saying that when you're talking about a distance being different in the south, based off of how it looks in the north, I'm saying if you're using a latitude and longitude coordinate system, there's no difference. It will visually look like a longer difference, but you could take the same exact distance in the north, transpose it in the south. It's just a math function. It looks bigger. It looks like it's a bigger thing because it's projected out and stretched out. That's a function.
And
of
you're
the map.
right.
It's,
The
it's
north,
not, it's not physically a different distance when referencing the coordinate system.
but all the lines of longitude converge on the north, so they must do the same in the south then.
Yeah,
but they expand. So the
you're
reason
looking
they
at
do
a projection, Jeran. I don't.
right, it's a projection of a globe.
It's a projection of a coordinate system of two hemispheres merged together. We just went over the ground curvature that
and
would,
so the way
that would
we
be
can tell
required to
that we-
substantiate if
so-
it's actually a globe, and there's 4 million miles of no curvature, bro.
Man, it's just
Like-
you're not getting it. That these people around the North Pole could stand together and hold hands, and they would actually be touching hands. In the South Pole, the same thing is true, but on this map, it's these people are completely separated from each other. So to bring it back to reality means we have to bend that outside back to a ball. You grab it and wrap it around there, and you'd be back to where the reality is.
Show me your hand holding party, and I just showed you that there's no curvature for 7 million meters.
Yeah, well, you showed me that there's no change in the height of the sun off the Earth, which I wouldn't expect one. It'd be like you looking at an airplane and saying, "Hey, that plane that's flying 35,000 feet the whole time is flying flat." No, it's not. It's flying over the globe. It's staying the same distance from the ground.
Then how do the stars and sun set, bro? The whole model's predicated on the physical elevation change. That's why the congruent triangles for the celestial theodolite shouldn't be possible. That's why what he showed with the eclipse stuff, there should be a giant arc for both of them. Let me show you this real quick, dude. We have it simulated out to scale.
Oh, I did say I would read super chats, and I didn't get to that. But my point is that we can. So we have to be able to test what somebody tells me the Earth is. Okay, so if somebody tells me that the Earth is flat, and I say, okay, what is it laid out like? Are you saying that there is no answer to that, or is it laid out kind of like this? The real Earth that we live on. I'm not asking for sky coordinates or anything. I'm just saying the real Earth that we live on. Is it, if we were to get above it and look down, would it look
it
like
probably geographically looks something like that. The coordinate system that we use, though, does not represent that.
right? But because the coordinate system that we use wraps around to the bottom of the ball, meaning that this location is the same for everybody out here. That's our coordinate system, right? No, I'm asking you.
Respectfully, though, think about this. If it wraps under a ball, right, there's going to be a physical elevation changes in the true positions of the bodies. And that's never present. That's what we just substantiated. So however it works, falsification is independent of replacement. And that's the sentiment that you previously agreed with not so long ago. So I don't know.
I do agree with it. So if you are able to refute the globe in a way that has no answer, how? I just gave you the answer.
No, your answer conflicts with how stars set. Like think it through. Somehow they all stay the same elevate. Like, bro, regardless of the angle that they're viewing it with, he derived the same elevation. So it should actually be a different angle going down following the celestial sphere. If you can see the screen share that I'm showing.
Well, you're saying for one person, let me just ask you. So you're talking, if the globe guy, hold on, what are you showing?
Okay, I'm showing a simulator of what.
Where are you showing? I'm showing it. What are you looking? What are we?
Sorry,
Oh,
sorry.
Yeah, I see.
Real quick.
Sorry, I thought you were talking about there. Okay, gotcha.
Yeah. So look at this. On the top here, we have flat Earth. On the bottom here, we have globe Earth. The celestial bodies changing in elevation following the celestial sphere is how this should work for an eclipse. These two bodies should be changing in physical elevation relative to each observer as we calculated. There should be a change in this physical elevation. But what actually happened for each person, right, regardless of the angle, came out to be the same elevation every time. That's what he was talking about when he said we're going to have to look for consistency across the data set for the elevations because we don't know what the elevation should be, but can we calculate the same elevation? For all observers, for all 6,200 some data points, this is the end result of this, that they travel parallel to the ground. There is no answer for this on the globe. The whole globe is built on this happening. They tell us this is happening. Before the celestial theodolite,
what do you mean, what's happening? You just keep saying words. So what do they say the globe is? Nobody says we live in the middle of the globe.
For the globe,
okay.
For the globe.
I know that's where they take the observations because it's the same thing. But okay, we say we live there.
The physical elevation change is represented by this. So you're on a globe.
Represented by what? That little dot?
This is the celestial sphere for the globe.
Okay, but how would I know that? How would I know you're not showing me the Earth?
I'm trying to tell you that right now.
Okay.
I'm telling you that right now. It's labeled globe Earth here, right here. But anyway, I know it's really small, but anyway.
So you're talking about, hold on, so that blue circle is the celestial dome, or the blue circle is the Earth?
The celestial sphere.
Okay, got you.
Okay, so
and then you have somebody on the top of it. What's that person up at the top doing? What's that line?
The person on the top. This is a separate thing. This is for flat. This is for flat Earth. This is what an observer would see, just on the surface of the Earth.
Got you. So he's standing there flat Earth, and then as the thing moves away from him, it is changing height, right?
Well, the apparent positions, as they're mapped out, they appear to be changing height, but the actual elevation that's derived comes out to be almost no change.
But not from the same location. I mean, because you agree that the sun is moving away from you, right? So how could it stay the same distance from every person? If I'm looking at it and it's moving away from me, hold on. If you're talking about at the top is a flat Earth, so that person, isn't that sun changing distance for that person?
Yes, apparent.
Okay. But you're saying it doesn't really change position. It's the same height all the time.
It doesn't change in elevation. Yeah, correct. We perceive it arc and go down. Like we perceive this, right?
Right.
And the globe also says that this is physical, but this is actually what was measured and what was plotted out and what happened.
I thought you said it measured the same distance at all times. It can't. You're looking right there. We can see it change distance.
The same altitude. Every observer.
It's changing. We can see it changing. We can see it changing.
And it's the same altitude for every observer, bro. That's why it's.
We can see it changing.
Where are you seeing it change?
Okay, so watch when it starts moving here. So that's going to be a certain height away from that person. Now as it moves, it changes height. That's changing. It has to change height right now. It's moving far away from him. I don't get how you don't understand this. If that you're telling me that light up there is staying the same height from the people on the Earth.
Yes.
Observer. Okay.
Always.
So, okay, but on this example you're showing of a flat Earth, it doesn't do that. You're moving it away and it's changing height away from the person on the Earth. Look at it grow. Now it's going to shrink.
Yeah. Did you see the scale of the change? It changes by like 10,000 meters. Like there's almost no deviation here. They consistently produce the same height for every observer over the 6,000 data points down to 0.01 of a change in deviation.
At the same time or at different times?
Different times throughout the whole course of the thing.
Right. So it's just basically calculating that for each person on the Earth, the sun and moon are always the same height above them. If you wait until it's above them.
Dude.
You're not explaining this well, though. You're not explaining. If you explain it like I'm a beginner, then. Because what you're saying is not making sense. If you're saying that on a flat Earth, that the sun and moon stay the same distance away from an observer when it moves away from you, is that what you're saying?
No, man. I'm sorry.
Okay.
It's calculating it for every observer across the whole path length of 7 million meters.
Right.
What every observer would see. And what it comes out to is that it doesn't change in elevation.
Okay, so wouldn't we get the same answer if we looked at an airplane?
No.
An airplane flying at 35,000 feet that is flying, and you took its distance away from anybody standing on the Earth at any time, then everybody would get the same height. The plane is flying 62,000 feet or 32,000 feet above them.
You would get different elevations.
How? If you're, that's what I'm asking.
Because it has different angles.
Because
So
it's moving.
It's a function of the rise and the run to it. So all we're doing here is changing the distance and angle, and it comes out to be the same elevation every time.